Good morning to all our participants for today in the third day of the second week of this Astro School TwoinColo. It's a collaboration between the University of Leiden and University of Antioquia. Today we will continue with the third lecture from Cristina Garcia Vergara, who is talking about the large scale of the structure in the universe. Cristina, thank you very much. A good afternoon for you, and the space is yours.
Thank you, Esteban. I'm going to share my screen. Okay. So thank you. I'm happy to be here in our third day of the school already. And thanks for some of the people that has been sent me the results of the workshop 1 and 2 and the plots. Really nice, and I encourage you to send me more results for the people that has not done yet. Then please feel free to also ask me any question by email. Okay, so today we are going to talk more about observational results of clustering of different population of galaxies. In the first lecture, I more or less explained like a big overview about how structure grow over time. In the second lecture, I gave more details about how can we measure the clustering of sources in the universe, in the space, and what are the more important parameters of clustering measurements. And today, the class will be much more focused on a review, or kind of review of observational results, and what can we interpret from those results. Of course, the review will not be complete. I will try to cover most of the most important things, but of course, I cannot show 100% of the results related with clustering. Then I will focus more on what I think is more important. Before to start, I'm gonna just show a couple of slides related with what we talked yesterday. And yesterday we defined the two-point correlation function as the most important mathematical way to describe the clustering of sources in the universe. We define the two-point correlation function as in this equation, which measure the excess probability over a random occurrence of finding a galaxy in a volume element dB at a separation r from another galaxy. I explained you that we always measure clustering comparing with our uncorrelated population, then with our randomly distributed objects. And I also mentioned that clustering depends on scale. We talk about the shape of the two-point correlation function that is normally observed in different surveys. We talk about the two important parameters of the correlation function, the correlation length and the slope. I'm gonna talk a lot about those two parameters today. Then I just wanted to remind that the correlation length R naught is just showing how is the amplitude of the correlation length, of the correlation function. And in general terms, a higher value of R naught means a more clustered population and a higher value of the two-point correlation function. And the slope is, I'm showing here the effect of the slope in the two-point correlation function. We normally find a typical value for the slope of around 1.8 for most of the populations in the universe, but still we can find some small variations, which just make the slope steeper or less steeper here. Also, one way in which you can think when we talk about R0 values, R0 indicates more or less the scale or the distance at which you expect an enhancement of objects around one specific object. Okay. Then our larger distances than R0, you don't expect to detect much more objects compared with the average in the universe. That is, you can think on R0 like in that way. And also yesterday I described two types of correlation function that we can measure depending on what is the available data that we have. Then I mentioned that if we have 2D position of the sources, we can measure the called angular correlation function. In that case, we don't have redshift, then we are projecting all the information in the sky plane, and but we can anyway measure the R0 and gamma parameters, which will be a little bit more uncertain, but still we can measure those. And in the ideal case in which we have 3D position, then we have rich information, we can measure the projected correlation function. I explained you that we can never measure the exact 3D distance between objects in the sky, but we can, with Redshift, we can make a much better estimation of the R0 and gamma parameters, and is less affected by projection effects. Yeah. Then that is what we talked yesterday. And in the class today, we are going to talk more about observational constraint of the clustering of different populations. As I have mentioned, large surveys of galaxies or sources are needed to really measure the correlation function with small uncertainties. Then I'm going to talk a little bit about what are the more important surveys that we have. And also, I'm going to show you the main important results of the clustering measurements for galaxies and also for other populations. I'm going to cover also a little bit clustering of some populations that we can detect at other wavelengths, not only at optical wavelengths. And I will try to show you what is the state of the art with the measurements so far, and what are the more challenge things that we are facing. And finally, as the title of this lecture today, we will study and I will show you how clustering depends on galaxy properties. Okay, so I'm gonna start focusing in optical wavelengths first, because at optical wavelengths is where we have more knowledge about clustering. Even when I said that 2D position are useful to measure clustering, rich information is crucial to have a more precise measurement. Then here I'm showing, I'm summarizing some of the redshift surveys in optical wavelengths. Those are redshift with, surveys with 3D positions of the galaxies that has been developed over time, starting in 1985 with CFA. I already showed this in the first lecture. This is the distribution of galaxies that we had at that time, with only 2,000 sources at that time. And this, the effort that has been done, have been being revealed here in the increasing number of sources that we can detect on surveys over the years. Then the most known survey that we have today, the most important and the largest one, is the Sloan Digital Sky Survey, which at 2009 had already around 1 million of galaxies on it, and now currently we have more than 2 million of galaxies. Then this kind of surveys allow us to really map the space, the local space in this case, pretty well. And I say local because Sloan is covering very large areas, but it's not that deep. Then we can reach redshift. We can explore mostly the local universe with Sloan. However, I will show later that with Sloan we also can explore high redshift for in the case of the more luminous sources. I would like to mention also that in general, surveys are flux limited. That means that we are just detecting objects until certain flux. But as you know, the luminosity, which is the intrinsic property of each source, is not flux. Then we are only able to detect the most luminous sources at high redshift. Then if we really want to compare, for example, the clustering of galaxies at different redshift and the dependency of the luminosity, we need to really take that in consideration and create volume limited samples, because otherwise we should be comparing pears with apples. Basically, because at high redshift we will be tracing just the more luminous populations, and at low redshift we are tracing a wider area in luminosity. Okay, so this is just to show you what is the coverage of the Sloan Digital Sky Survey. This is the spectroscopic coverage, but we have photometric information over all this area too. It's just to show you that it's covering a huge area in the sky, specifically 14,000 square degrees. Then it's a huge area which allows us to make a lot of measurements of clustering, and we can learn a lot from this survey. And that is the reason why most of the clustering measurements that we have so far are based on Sloan data. Okay, then I will talk about the dependency of clustering on galaxy properties. Then it has been observed that the clustering depends on galaxy properties. Then different type of galaxies has different level of clustering. This is and a spoiler, then I will show you the results in detail, but in general, we found that more luminous, optically red, early type, bulge dominate, higher stellar mass, and low star formation rate galaxies in general are more clustered than their counterparts. Then they are more clustered than the less luminous, the optically blue, the late type. This dominated lower stellar mass and higher star formation rate galaxies. That is a general trend that we can find. This is just at a fixed redshift, because clustering also depends on redshift. Then when we compare clustering, we have to focus on the same redshift if we want to compare different populations. Then this is the projected correlation function for galaxies in Sloan at different absolute magnitude range. This was measured by Sehavi in 2011, who used around 10,000 galaxies over 8,000 square degrees. And he focused on galaxies at redshift lower than 0.25. And we are talking about local galaxies. Then they split the data in different magnitude, absolute magnitude for the samples, and they found that the correlation function clearly increase with increasing the galaxy luminosity. Then here in magenta, you can see the brightest sample, and this cyan should be the fainter one. Then the other conclusion that they have is that the slope is more or less similar for all the subsamples. Then the slope don't vary so much, but what varies is more the correlation length. And also the variation is not that strong for fainter galaxies, but as long as you are going to explore brighter galaxies, this increment in the R0 parameter is much more strong. Then I will give you more details about the interpretation of this tomorrow in the lecture tomorrow. But basically, the conclusion that you can obtain from this result is that more luminous galaxies reside in more massive dark matter halos than less luminous galaxies. In general, when we are at a fixed redshift, a higher R0 value corresponds to a higher mass for the dark matter that hosts the population that you are studying. For now, just read it in that way, but we will understand why we can make this conclusion tomorrow. Regarding the dependency with color, this is again the distribution of galaxies in Sloan. And the color in this plot is actually indicating the optical color of the rest frame color of each source. Then red are redder galaxies and blue is bluer galaxies, or green in this case. Then already by eye, you can maybe realize that red galaxies tend to be very concentrated in the filaments of the large-scale structure. And in the other hand, green galaxies, which are more bluer galaxies, are more smoothly distributed over the space. They still are more concentrated in over densities because, of course, this is the large-scale structure of the universe, but they are less accumulated in filaments. And in the case of red galaxy, we can see that more strongly. And that can be actually measured computing the clustering of the sources. Then this is, again, Sehavich at 2011, who measured the projected correlation function for red and blue galaxies in Sloan for different luminosities. Then if you compare all the bulk of curves here with this one here, you can already see that in general, you have lower clustering for blue galaxies compared with red galaxies. But also, we can see the trends if we split this in different luminosities, which is more or less what I showed you in the previous slide. Then in which brighter galaxies are more strongly clustered. Then this relation means that if we think on a fixed luminosity, red galaxies reside in more massive dark matter halos than blue galaxies. Here I'm showing more or less the same, but this is just for a fixed luminosity. And if you split the sample in red or blue galaxies within a fixed luminosity, you can also clearly see that we have red galaxies much more clustered compared with the blue galaxies. Also, here in this plot, we can see that the amplitude is clearly different, but the slope of the red galaxies decline faster than the slope for blue galaxies. Then that is a very interesting behavior, and we can see this here much better. These are the same paper, but here we are looking for, we are seeing the correlation length as a function of luminosity for red galaxies, for blue galaxy, and black is all galaxies together. And here we see the slope as a function of luminosity also for blue and red galaxies. Then, as we saw before, in general, blue galaxies are always less clustered than red galaxies. But here we can see an interesting trend because blue galaxies are increasing their clustering at higher luminosities. However, for red galaxies, this is more or less flat at faint luminosities, and this start increasing just for the brightest red galaxies. And we also see a similar trend here in which the slope of blue galaxies don't vary strongly with luminosity, but for red galaxy, we have a much steeper slope for faint red galaxies. Then this trend was not so expected, but then the interpretation of this is that faint red galaxies are mostly located in cluster of galaxies. Then basically when we split the sample in red and blue galaxies, the faint red galaxies are mostly inhabiting very massive dark matter halos, which are the cluster of galaxies. Then given that they inhabit those massive dark matter halos, then we expect that they have a stronger clustering compared with the blue galaxies that shouldn't inhabit cluster, but can be in the field, let's say. Then that is a reason why we don't see the same trend for red galaxies compared with blue galaxies. Yes. Okay, then so far I just show you the results of this kind of dependencies for redshift 0 or for the local universe. But Coyle et al. 2008 studied also these dependencies at redshift 1, and they find a very similar result. Then basically red galaxies, if you compare like in this way, this is the measurement that they made at redshift 1, the solid line, and red galaxies are more clustered than blue galaxies in general, and we see the trend in which the clustering is also increasing with luminosity for both red and blue galaxies. In this case, the flat trend that we saw at redshift 0, which are shown here as these dotted points here, is not that strong because at redshift 1 you have much less cluster of galaxies. They have not been formed yet, and also because this plot is also showing like more luminous numbers here. Then you are going not so faint because, of course, at higher redshift it's harder to detect fainter galaxies. Then in this case, we are tracing luminosities of 0.1, but at higher redshift we are just tracing the more luminous one. But in general, the trend is pretty similar. This is another study of Coyle et al. 2017, who studied the dependency of clustering with stellar mass for galaxies at redshift 0.5, a galaxy at redshift 1. They used, in this case, data from the Primus and Deep 2 galaxy surveys. And here I'm showing this plot. This is the stellar mass as a function of bias. I have not defined bias yet. I will define and explain what bias is tomorrow. But for now, just assume that this is more or less the correlation length. Bias is similar to correlation length at the same redshift. Then the trend here is basically that more galaxies with more stellar mass are more clustered. Then this trend is also observed at redshift 0.5 and at redshift 1 as well. Then the trend is basically that galaxy clustering amplitude increases with increasing stellar mass, which makes sense. Okay, they also study the dependency on the specific stellar star formation rate. The specific star formation rate is defined as the star formation rate of a galaxy over the stellar mass, normalized by the stellar mass. But if you fix a stellar mass, the trend that they find is that galaxies with higher star formation rate are less clustered than galaxies that have smaller star formation rates. And this trend is also the same at different redshift, as they are showing here the result of different works. Then this is from redshift 0, redshift 0.9, redshift 1, and redshift 2. And in general, the trend is always the same. Then you have higher clustering for lower star formation rates at a fixed stellar mass, because as I said, stellar mass also depends on clustering. Okay, then so far, this is the summary that I have been trying to show you with the current results. Most of them compute from Sloan data. I show you the result about the dependency of clustering with luminosity, with the color of galaxies, with the stellar mass, and with star formation rate. I'm not showing you the plots for the early or late type or the bulge dominate or disk dominate galaxies, but the dependency is not so surprising because early type and bulge dominated type galaxies are also red, and we already saw that red galaxies are more clustered than blue galaxies. And it's not very surprising, but people have specifically measured this, and the trend is found when you measure their clustering. Okay, then now what happened with the clustering at other redshifts? This is actually a very complex question, because it's really hard to compare the clustering over redshift, because you cannot observe exactly the same object at different cosmic times. Then you cannot really see and the evolution of clustering for a single object. Then it's really hard to compare. But what we can do is to measure the clustering for similar types of population at different redshift and see what is the trend. And in general, I'm showing the dark matter distribution in the universe, as I show you this in the first lecture. If you go to the right here, you are increasing the redshift, and this is the local universe, this is the early universe. And intuitively, if you know that matter over densities grow over time, you could also think that the clustering of galaxies will increase at lower times. I mean, at earlier times, I will expect like a weak clustering, because the particles are not so strongly grouped. But as long as you go to lower redshift, I can see by eyes only much more clustering of the structure. And that is actually more or less true for dark matter, but we will see that that is not what we observe for galaxies or baryonic matter. The reason of why that we will explain tomorrow. We will talk tomorrow about that. But today I'm going to show you what we are observing. Okay. Also, given that I'm going to show you some results about high redshift, I had at high redshift, we can detect different type of populations. Then I also will try to introduce a little bit every different population, because I'm not sure if all of you know them. Then I will try to be clear explaining that. Okay, then first we'll start with the clustering of Lyman-Break galaxies. Then Lyman-Break galaxies are star-forming galaxies detected at high redshift, normally greater than 3. And those kind of galaxies has a very strong UV emission, then because they are forming stars. Then here I'm showing a simulated spectra of an LBG, which normally has Lyman alpha emission here. You have the UV continuum here, and you have a strong break in the continuum here, just in the side of Lyman alpha emission. And this break is produced because the absorption of neutral hydrogen in the intergalactic medium when those photons travel to us. Then because the high universe has a lot of neutral hydrogen, all this emission is absorbed in the way toward us. Then those kind of galaxies can be detected just because this feature in the spectra, but they are photometrically detected, or actually using bands as the ones that I'm showing here. Then normally the detection of Lyman-Break galaxies is based on imaging, not in spectra. Then we normally don't have redshifts for those sources. Then Uchi et al. 2004 measured the angular correlation function for Lyman-Break galaxies at redshift 4 and 5 using data from Subaru Deep Survey. Then, given that Lyman-Break galaxies are not that bright and they are a very high redshift, those kind of galaxies are normally not detectable in Sloan, for example. Then you need to use more specific surveys that are pretty deep in optical wavelengths. Then in this case, here I'm showing the angular correlation function. This is for the sample at redshift 4, and these two are for the sample at redshift 5. One interesting thing that you can already see is that the error bars in the measurement increase a lot at higher redshift, and that is because at redshift 4 they are using around 2,000 Lyman-Break galaxies, and at redshift 5 they are using 300 for this case and 100 for this case. Then you can already see the impact on the error bars when you are computing correlation function using so few objects. But in general, they find they can compute a correlation length for their measurements. Also, it is found that brighter Lyman-Break galaxies are more strongly clustered than fainter Lyman-Break galaxies. Then that dependency on luminosity seems to keep at high redshift too. And here I'm showing the correlation length that they obtain for the samples of Lyman-Break galaxies, which are shown here in this square. Then they had two measurements, a redshift 4 and a redshift 5. They also include a measurement available from other study, a redshift 3. And here they show they are not for local galaxies, just for comparison. These are star-forming galaxies. All of them have more or less similar luminosity, because that is important, because clustering also depends on luminosity. Then this is for a more or less fixed luminosity. And what we can observe is that the clustering or the R naught is relatively constant over time from redshift 3 up to redshift 5 for Lyman-Break galaxies, then it's not evolving at all. And also the R0 value that they measure is not that different than the R0 of star-forming galaxies in the local universe. Then given that Lyman-Break galaxy also are a star-forming galaxy, then they should be similar populations. We in general can see that there is not a strong trend in or evolution in the clustering of star-forming galaxies over time. Okay, we have another object, very interesting, that we can observe at high redshift.
Excuse me, Christina, you have a question in the chat before you continue.
Let's see.
What could be a reason for the low specific star formation rate galaxies to be more clustered?
That is very interesting question. I'm gonna try to go there. This one. Yeah, well, in this paper, actually, you can find a very detailed interpretation about this result. I didn't want to show this here because it's a little bit more specific, but there is a relation between stellar mass and star formation rate, which is called the main sequence for galaxies, in which you can see that galaxies normally with galaxies with higher stellar mass have higher star formation rates. Then if you measure the clustering of star formation rate, you're basically constraining the dark matter halo in which the objects inhabit. And then given that they find this result, they interpret this as how to say this, like as the way in which galaxies evolve in this main sequence relation. Then basically they said that galaxies with low stellar mass and high star formation rate normally evolve through higher stellar masses and lower star formation rates, right? Then this tells you something about how galaxies evolve over time with respect of your star formation rate and stellar mass. Maybe I can show up a plot tomorrow to explain this better, but it's very an interesting question. And yeah, I don't know if I will try to show up plot for this tomorrow because it's very nice. It's a very nice result. Okay, then yes, the clustering of quasars. Then I hope most of you know what a quasar is, but if not, I explain this here with this nice image where this is a artistic representation of a quasar. Quasars are extremely luminous active galactic nucleus, AGNs, in which you have a supermassive black hole in the center of in the very center, and you are accreting a lot of material around the supermassive black hole. Then this is dust, gas, which is being accreted here, and this generates a huge amount of luminosity. Then quasars in general are very powerful objects, very energetic objects, and because of that also they are very luminous, and we can detect them even if they are at very high redshifts. Then even with Sloan Sky Digital Survey, we can already detect quasars at a high redshift. This population peaks at redshift around 2.5, but you can find quasar at very different redshift from even in the local universe, and also at redshift, I think the highest one has been found at redshift 9 or 10 or something like that. Then you can find those at very, very high redshift too. And the other important characteristic for a quasar is that you can detect it at almost all the wavelengths in the electromagnetic spectrum. Then they emit in X-ray, in radio, in infrared, optical wavelengths, then you can detect those at very different wavelengths. Okay, then Shen et al. 2007 used a sample of around 4,000 high redshift quasar in Sloan with redshift greater than 2.9. And this is the projected correlation function because they had also redshift for the quasars, precise redshift. They split the sample in two redshift bins, one at redshift greater than 2.9 and the other at redshift greater than 3.4. And again, of course, this is a very noisy measurement because we have a few quasars only, but still you can see that the red points here are significant, are systematically above the black points here, and they actually measure the R0 for both samples. Then the message here is that at higher redshift, the clustering is much more strong than compared to lower redshift, at least for redshift greater than 3. And also they study dependency on luminosity, and not only them, but also several other people have been trying to understand the dependency of clustering with luminosity in quasars, but so far there is not significant evidence in which we will find that more luminous quasar have higher clustering, as in the case of galaxies in the local universe. And that is still being studied, but so far there is not a clear dependency on luminosity. But we have also to keep in mind that these kind of objects are not like galaxies. These are very extreme objects, and the luminosity of a quasar is also very related with how the material is being accreted here in the supermassive black hole. Then the luminosity could be have a different physical reason compared with a galaxy. Then we could expect a different trend there. The same study, but here I'm showing the correlation length as a function of redshift. And what we find is that in general, the clustering of quasars is relatively flat until redshift 2. But then after redshift 2, the clustering is strongly increased up to very high values here at redshift 4. Here we are talking about 25 megaparsec over 8, which is much more higher than all the other values that I have been showing you. Then quasar redshift 4 actually are the most clustered population in the universe at this redshift, and therefore this means that we expect that they trace the more massive overdensities at redshift 4 and inhabit in the more massive dark matter halos at redshift 4. Again, this kind of interpretation can be done after a lot of complex physics that I will try to explain tomorrow. Okay, and so far I have been talking about the clustering of sources that we can detect at optical wavelengths, which is where we have most of the available data. But as you know, we can also observe at other wavelengths, and we can detect other type of population at other different wavelengths. The problem is that at other wavelengths, this has not been so much studied because we don't have availability of large and deep surveys to really make so many measurements of clustering. But still, this has been progressing a lot over the last years with the arrival of new instruments. And here I'm going to try to summarize some of the most important results of clustering of population detected at other wavelengths. This is not a complete summary, but for example, at infrared, we have Speedster, which can observe, and actually it has been covering large areas in the sky, and we can detect a different kind of population in infrared, which, for example, ultraluminous infrared galaxies, that maybe you have heard about that. If we move a little bit into submillimeter wavelengths, we have some instruments, for example, Apex, but also Scuba, more recently, Scuba 2, and of course ALMA, which is a very great instrument. Unfortunately, with ALMA, we cannot make so big surveys because the field of view of ALMA is more smaller, but it still will make important improvements in this area of study. And the objects that we can detect at submillimeter wavelengths are the known as submillimeter galaxies. I will talk a little bit about this later. And finally, if we go to even longer wavelengths, we can study in radio wavelengths. There are several more surveys at radio wavelengths, actually, like, for example, VLA and VSS. LOFAR is right now in process and is generating a lot of new catalogs, and SCA will be coming in the few next years. Then we can have more clustering measurements at radio wavelengths, actually, because we have more surveys, and I'm going to talk about that later too. And we can explore two different populations at radio wavelengths, mostly AGNs and star-forming galaxies.
Excuse me, Christina.
Sure.
You have a question in the chat. How could blended sources affect clustering in submillimeter surveys?
Wow, that is really, really interesting question, and is actually something in which I have been working. In some more slides, I will be talking about submillimeter galaxies and about the clustering of submillimeter galaxies, and I will answer your question because I need to explain a little bit more. But just to make a fast answer right now, the blended sources and the angular resolution affect strongly the clustering that we can measure from submillimeter galaxies. And in that sense, all the surveys that are not very precise and have a low resolution normally could overestimate the clustering of sources. And this has been shown now recently using ALMA data. But I will talk more about that after the break, probably. Then, yeah, for now, I will stop here. After the break, I will go through a little bit through this. I'm not going to talk about the infrared surveys because it's not my expertise also, but I will focus more on what can we observe at submillimeter wavelengths and at radio wavelengths. Then, yeah, that is all for now, and see you all in 15 more minutes.
Thank you very much, Christina. I don't see right now any other question in the chat. So we are 10 minutes ahead. So we have 15 minutes break. So we can reconvene at 9:05 Colombian time, 3:05 your time in Europe. Thank you very much for all the participants, and see you in 15 minutes.
See you. Bye.